Right, we're good to go.
Okay, ready? Great. Yeah, I'm Kenny, and I'm from the Chemnitz University of Technology. And yeah, the topic of my talk is going to be about encoding time series using HTC and VSA. And I plan to show you some of our work, not very technical details, but just for an overview to get a feeling what we have done so far. So, but first I go into this topic, I would like to tell something about our background and our team. So we are working in the field of mobile robots. Here you can see two of our robots working in an unknown environment and trying to collect some objects. So that's a standard application of the mobile robots. And we are on the perception field, so computer vision, sensor processing, and so on. So hence we have, for example, those three topics, like time series analysis, because we are working with sensors, and the sensors producing signals over time. Then we are in the field of visual place recognition, so image processing and robust sensor fusion and other topics as well. But I also highlight these three topics. And I'm rather related to the time series task, and they are not only related to the mobile robots, but also in a broader view with autonomous driving and advanced driving assistance systems. And that's why I want to give you a brief or a short application where we can use time series analysis in this topic. So imagine we have an autonomous system which produces, or which has some sensors and produces some signals over time. In a recent project, we had tried to analyze scenarios in an urban street or scenario where we analyze the recorded data by the car. And where we try to classify different scenarios. And the goal was to structure somehow the mass of recorded data into known scenarios and use them for testing algorithms later. For example, and this here is finding a scenario where the cars turn right and almost crossing a pedestrian. Okay, hence the main topic is related to time series classification. So we have some signals, do some encoding, and can classify whatever. And yeah, and within this task, I'm interested in the temporal order encoding of the time series, because I think encoding of temporal order is a key component for many applications. Even transformers are using positional encoding for their embeddings. Yeah, and within this specific pipeline, I mainly focus on the encoding part rather than the classification. So that's the overview slide. So I just organized different topics into this picture here. I will shortly touch each, and somehow to visualize topical threads where we started and where we are now. The green dotted boxes are somehow work in progress. And yeah, I would start with the very first application where we incorporate HTC for time series analysis. It was related to driving behavior classification. So we have a data set which recorded different sensors in a car. And the goal was to classify the driving style of the driver itself. And in the literature, so it was done with an LSTM network standard procedure. There we had an idea to, what is if we use HTC to somehow encode the time and the sensors, and can neglect the LSTM. So replace the LSTM by just encoding the whole series with HTC. Roughly speaking, we used fractional power encoding to transfer the scalar values of the sensors into high-dimensional space, and using also high-dimensional vectors for the timestamp, bind them together, bundle, and get an overall vector for the complete scene, which contains the whole time. And we have seen that it's a faster learning. It's possible to learn faster without this LSTM. It's more data efficient, as you can see on the left graph. I get it's a little bit tiny, but yeah, there we plotted the dependency of amount of training data. So the HTC approach needs less data than LSTM, and it's more robust against noise on the right side. So we did experiments with some missing sensor values. Yeah, it was the very first application where we just tried to incorporate HTC for encoding the temporal order. And from there, we are going to the next step, because after doing this application, there was a publication related to a state-of-the-art classification algorithm, namely MiniRocket. There we have also seen some connections where we can use HTC to improve this method. And MiniRocket is, as I said, a standard method for state-of-the-art method for time series classification. It's really fast and efficient, so do not use any deep learning models, but it uses a lot of random kernels, filter kernels, to get somehow features from the time series. So as you can see on the left, there are some filter responses, and all the responses are per time. So per time, a high-dimensional vector with the filter responses, roughly speaking. And at the end, it's sum over time to get an overall feature embedding of the whole time series. And summing over time has the problem that we lose the information of the time for the specific feature embeddings. And that's why we thought it might be a good option to incorporate the timestamp encoding that we have done in the application, which I have shown previously. And yeah, you can see it on the picture on the right. So just binding timestamp to these high-dimensional vectors with a MiniRocket. And it helps a lot for data sets which are where it is important to have the temporal order. For example, here our results on the right, we did some experiments on synthetic data set where it is a classification problem with two classes. Either a prefix in the first half of the signal or in the second half, so it's really important to get the global position in time. There, MiniRocket was not able to distinguish between the two classes because it's sum over time. And with this HTC and extension, it's possible to solve this problem. And also in real world problems like the UZR benchmark, we can see that for some data sets it's beneficial to incorporate this temporal encoding, and we were able to improve some data sets up to 12% in accuracy. Yeah, and I forgot to say that while creating these timestamps, we had the option to adjust the created similarity of neighboring timestamps. So as you can see here on the picture, it's also really small, but yeah, we have a parameter where we can adjust the slope of the created similarity between neighboring timestamps. And finding the correct hyperparameter has to be done for each data set individually, and we did it with straightforward grid search, so with iterative testing. Okay, going from there to the next step is that after doing this application, there are some extensions from the author group of MiniRocket. So there are some other approaches like MultiRocket and Hydra, and these are extensions based on MiniRocket. And roughly speaking, MultiRocket is MiniRocket with multiple pooling, so not only summing over time, but also doing some other things. For example, also a global position encoding or somehow global position encoding. But there's a problem that is ambiguous because I don't want to go into details for the sake for understanding. It's ambiguous, and that's why it can also lead to misclassification. Hydra uses a dictionary-based approach, just find random shapelets and building histogram over time, and it's the same problem as in mini-rocket. You are losing the temporal order of the bins of the histogram. Hence, or that's why we also try to incorporate this explicit time encoding into these two approaches, and we're also able to improve classification accuracy for multi-rocket and for Hydra. And additionally, we also increase the computational efficiency of multi-rocket because multi-rocket uses 4 pooling operations, and with this HTZ incorporation, we were able to replace some pooling operators because they are not necessary anymore. That's why it's also faster than the original mini rocket. Yeah. Okay. I said that finding the correct hyperparameter for the created similarity of the timestamp is done by grid search. This is really what it did. This requires a really high computational effort because you have to go iteratively through all combinations. So that's why next thing we did recently was trying to improve this hyperparameter fitting. So as I said, grid search is high in computational effort, and a possible solution is, okay, we can use HTZ, bundle all possible scales, and let the classifier decide which one is the best. It works for some data sets, but for some data sets, it leads to misclassification, maybe based on the crosstalk noise from all bundled scales. So it would be nice to clean up these overall representation to remove the misclassifying representations. And to do so, we tried a solution with computing and superposition. I guess it's too tiny to see here. No, it's okay. However, as I said, we have our embeddings from mini-rocket, for example, for each timestamp, and our timestamps bind them together. And in these timestamps, there are now all the possible scale representations bundled. Then feed the result into a classifier, and we are getting a rate matrix, which can be seen as a set of prototypes for each class. And you can compute the scores for a specific sample embedding by just multiplying them and selecting the high score and so on. And now we can maybe use these class prototypes to look, okay, what's the probably best scale which was selected by the classifier by trying to somehow backward interpret the class prototypes and remove the unnecessary scale representations. And to do so, we need our embeddings for each scale, and to avoid computing the embeddings for each scale individually, we can use an approximation based on the original mini-rocket features bundled and binded to the bundled timestamp from the specific scale, which creates an approximation of all pairs between them. And then we have our approximate embeddings for each scale and can compare it with a dot product to our class prototypes and based on the scores, we can decide which scale might be the best option and remove all the others. So just roughly speaking, I don't want to go in more detail. I hope it's somehow clear. So yeah, if there are questions, we can talk about later. And we have seen it is with this way, it is possible to find the correct scale, even for those data sets which are hard if we just bundle all the scales. And yeah, but it's still work in progress. There are some small problems, and we are trying to fix. And yeah. Okay. Another application, it was also, which was, yeah, another application was a little bit a X-course. It was also mentioned by the talk from Ross this morning. There we participated in a challenge where the goal of the challenge was to detect epileptic seizures of people. Yeah, as I said, the goal is predicting a seizure within the next 15 to 75 minutes, only based on wearable devices. So you have not access to any EEG data, just hand-wrist sensors with IMU, pulse, temperature, blood volume, pulse, and so on. So you have multivariate time signals in a window with a length of 10 minutes. It was actually a huge data set with 130,000 samples, but only one person was positive labeled. So it's really unbalanced because yeah, epileptic seizures are really rare events. Yeah, we decide, so Ross, Dennis, here, and I decide to participate in this challenge with this HTC mini rocket approach. We modified it slightly because we have our input, our multivariate input, so different sensors, then just using the mini rocket approach without the temporal encoding per time step, but afterwards, well, it's a bit blurry. Yeah, I don't know why. So we have an embedding from the mini rocket, so it's the feature embedding, and then we are using this embedding and associated with the time of the day, as Ross explained this morning, to get a feature at a specific time embedding, and then feed them to a standard classifier to get a score between 0 and 1, so if there's a seizure or not. And the question, why did we that? First is, I'm not sure why. Okay. That's really good. Okay, why have we associated the feature embedding with the time? Well, in a publication from the authors, they figured out that the time is the most important feature for classification of these epileptic seizures. That's why we want to associate the feature with the time. And how did we do that? Yeah, we use these fractional power encoding with in a cyclic manner. So starting after 24 hours at the same point to get a full day cycle, like here on the figure on the right. Here, the results were that with the standard mini rocket, we reached a area under curve of the receiver operating characteristic curve of 0.55, and with this explicit daytime encoding, we were able to push up the area under curve up to 0.79. It's on the private test set of the challenge, and yeah, with this actually simple approach, we have also won the contest. So it's actually really cool that HTC helps to improve a method as well. Okay, that was a little excursus to some medical application. Yeah, the final application is somehow related to the first, so it's also in the autonomous driving area or advanced driving assistance systems, and namely, as I had mentioned at the beginning, we want to classify different scenarios. So here's a work where we did some scene representations or scene encoding. As you can see here on the left top corner, there's the picture of the beginning. So we have a scene from urban streets, and with all the objects, all the cars and the pedestrians and so on, and want to represent all the relations. And with MiniRocket, there's a problem for this specific application because MiniRocket is actually limited to equal sequence length and the same number of channels. So you cannot vary the channels. But in a scene like that, you have different numbers of objects, different numbers of cars, which you want to represent. And that's why we tried another encoding mechanism compared to MiniRocket based on HTC, where we can compute all interactions between all objects in one step. It's also using computing superposition, and we did the standard encoding is like that. Okay, you have different numbers of objects, and that example here 4. And the goal is to find each interaction between each object, so the relation between ego and target, and compute the position or the relative position and create embeddings for each entry in these metrics here. Then you can sum up over all representations and get your scene representation, or where you can do something like classification and so on. And the idea was that we can use specific mechanisms of HTC, like using the complex valued holistic reduced representations and the fractional power encoding. So we encode each object and each pose with this fractional power encoding and create 2 representations. First is binding the objects to its pose, and the second is unbind the pose from each object. The reason for that is that later on we can compute the representation R by binding R1 to R2, and having these unbinding in these computation leads to encode the relations between the objects, because unbinding in the FHRR, and especially if you are using the fractional power encoding, creates the relation, for example, the spatial relation in X, for example, X position. And that's why we are able to compute all relations of all objects in one step by just using these actually simple HTC operation. And it also turns out that it is possible to reach the same results as if we are using the standard encoding mechanism by just iterative combining all objects together. And that's a example of a really recent work we have done, and also doing this stuff. So it's also an ongoing work. And you have to also keep in mind that hypervectors have a limit in capacity, so you cannot process a lot of objects. So at some point you run into capacity limits, but usually it should be fine with the standard capacity that the vectors have. That was a brief overview of the work we have done related to this time series encoding. And thank you.
So we have time for questions before we.
So thanks a lot for the talk. So if you're using like Fourier holographic reduced representations, right, then there's like implicitly a couple of hyperparameters, right? One is the bandwidth and another is the phase distribution, which is the kernel choice, as you're well aware. So like, I'm just wondering, can you walk me through a little bit how you're choosing those hyperparameters, or are you using a multi-scale approach? Or?
You mean, for example, in the mini rocket example applications here, as I said, the choosing of the correct similarity is actually the related to the bandwidth,
right?
And we choose these parameter either by grid search, so iterating over different possible parameters and having a test set and choose the parameter with the highest accuracy, or as I have had explained on the last, these hyperparameter fitting, where we try to use a classifier, use the prototypes within these metrics, and looking what was the choice of the classifier, because we bundled all possible scales together. So, but yes, still the problem finding the correct parameter and also kernel. Yeah, we did also some experiments with different kernels. Get also different results. So some kernels are more beneficial than others. Yeah.
Sounds great. Thank you.
Talking about the challenge.
Yeah.
That you have won. So you show two results. And I guess your results and mini rocket.
Yeah.
But those are other methods involved in that competition, and did they show their own results, and what were the numbers?
You mean other participants in this contest?
Well, methods. Maybe you have participants with 10 methods.
Yeah, that's the point. For now, we do not know what is the area under curve from the other participants, so the leaderboard is still private. Yeah, it's an ongoing process with the organizer.
They have results, other results, not only yours.
Yeah, there are other results. Yeah,
but are they lower than mini rocket?
I don't know.
They don't show the results.
It's not disclosed yet.
Not yet. So the leaderboard.
They just show that you're a winner. And
yeah.
So,
we got the notification that we won the contest, but we don't know how. But it would be really interesting to see the other results. Yeah.
All right, we're all happy. Anybody else? No. Then I would like to thank you once again for your